And let me first say a little bit about how everything fits together, how all the computational stuff fits together. Um, one way to view it is you start with this. You start with solving quadratic equations with linear equality constraints. How do you minimize a quadratic with linear equality constraints? What does it reduce to? Is linear equations, right? And then we know how to solve linear equations. I actually know quite a lot about how to solve linear equations. Okay? All right, so that's just like done, right? Well, one way to view Newton's method is this. I ask you to minimize a smooth function subject to equality constraints. And what it effectively does, if you look above, if you look at, say, what is Newton's method doing, you could even write it so it was clear. This is what it's doing. The answer is it's solving a sequence, a short sequence of quadratic equality constraint minimization problems, right? I mean, if you were to profile Newton's method, what you'd find is it's solving linear equations. But the linear equations it's solving are actually solving a equality constrained quadratic minimization problem, right? So then you could say, well, we have now extended, we can now solve smooth equality constrained problems by reducing that to solving a sequence, right? In fact, not a long sequence, right? But a sequence of quadratic equality constrained problems, which in turn are linear algebra. Already got this? Well, guess what? Now we're going to go to inequality constrained problems, and guess how we're going to do it. We're going to take an inequality constrained problem, and we're going to reduce that to solving a short sequence of smooth minimization problems. Okay? So now you have a stack, right? And the stack will look like this. You have an inequality constrained problem. You will solve it by solving a 10, 20, the number doesn't matter, right? But it's not like a gigantic number, right? You're going to solve 10, 20 smooth minimization problems. How are you going to solve those? Each of those is going to be reduced to solving, again, a modest number of quadratic equality problems. Everybody got this? And solving a quadratic equality problem, that's actually something we have an actual method for. It's called linear algebra. Everybody, so this is the full big picture. Actually, if you wanted, you could put something on top. And the on top would be the kind of stuff that CVX does. That takes your original problem, which may have all sorts of non-differentiable functions and things like that, and automatically does the transforms to a problem which you can handle that has, for example, smooth constraints and smooth objective, right? So, for example, converts your problem to an LP. In an LP, all your objectives and your constraints are smooth. Everybody see what I'm saying? And now you see the entire stack, right? That's it. That's the whole stack. Okay? So that's the big picture, and that's what we're going to do today, or part of today. All right. So we're going to start with this problem, inequality constrained. And you know, the equality constraints are just going to float along everywhere we go, and you can even almost ignore them. And it's even, when I look at examples, I'll probably ignore the AX equals B, but it just floats along and doesn't really hurt anybody. Besides, we can handle it, right? In fact, it's the AX equals B that persists at all levels of this stack, right? When you go down the Newton's method, it's just linear equations, right? Each iteration of Newton's method, it fills in a row of a KKT matrix linear. So linear, or another way to say it is, if you write the linearize me method on that, when you have AX equals B and you call that method on AX equals B, very simple, it just returns itself. Okay, so, and that persists all the way to the bottom of the stack. Okay, so we'll make some assumptions. We'll assume that A is full rank, right? So we don't have redundant quality constraints. And we'll assume that there's a solution, right? That there is an X that satisfies this. And we'll assume strict feasibility. I mean, you don't even need a lot of this stuff, but this is your sledgehammer assumptions. And by the way, this is actually the Slater condition, essentially, here. You don't need any Slater condition for equality constraints, right? Because the modified Slater condition says you can ignore actually linear equality constraints. Well, that's the only kind of equality constraints you can have, and linear inequality constraints. So we ignore those entirely. And this says simply that the domain, the interior of the domain actually intersects. Well, actually, sorry, the domain is open because we're assuming they're differentiable, right? So it says the domain intersects the equality constraint, and this says things like strong duality holds and the dual optimum is attained. Okay, so what are examples? Well, linear programs, quadratic programs, QCQPs, geometric programs, right? Geometric programs, all the functions are things like log sum exp. Entropy maximization. So you say you want to maximize entropy, you get something like this, right? So that's a problem, looks like that. That's asking to maximize entropy or minimizing negative entropy. And fx less than g and ax equals b, you can even interpret, if you interpret x, say, as a probability vector, it doesn't have to be normalized here, but assuming it were, this says, please find me the maximum entropy distribution that matches certain expectations exactly and satisfies inequalities on other expectations. That's what this problem is. That's one way to interpret it. Okay, and this will work. This is fine. Oh, as I said, you may use one of the transformations, the kind of ones that CVX would use to take a problem with non-differentiable objectives, constraints, and transform it, in fact, in a completely mechanical way, to a problem that doesn't have, that where all the constraints are smooth. Like, for example, you transform it to an SOCP or to an LP, right? Okay. Now, cone programs, things like SDPs and SOCP, these are actually better handled as problems with generalized inequalities, although they will work here too, provided you express them in a smooth way. There's some really cool smooth ways to write down SDPs, for example. We've already seen the log barrier, but the key is to start with your original problem and do something really weird. It's this. We're going to take the inequality constraints and we're going to put them in the objective. And what we're going to do is we're going to take I minus, that is the indicator function of R minus. So that's a function that looks like this. It's 0, and then it goes to plus infinity if you go positive. Okay? And that simply says, it says that you take fi of x, and if it's less than 0, this returns 0. And if it is positive, it returns plus infinity. A plus infinity in an objective is basically saying it's infinitely bad, which is to say it's unacceptable, right? So this is the right, that's the idea. Okay? So now you can't apply Newton's method to this directly because this is like big time non-differentiable, right? Because you've got this thing that goes like up to plus infinity. Okay? So, so what we're going to do instead is we're going to make a surrogate that's smooth. Okay? And the surrogate that's smooth is the log barrier. So you'll form 1 over t minus log minus f. These are functions that look like this. Okay? They look just like that. Right? These are increasing values. So this one that hugs the true function closer is with a higher t, higher value of t. Okay? So now this one, that problem, that's Newton ready. Right? That's ready for Newton with equality constraints because it's smooth. Right? And not only that, at least visually, the approximation improves as t goes to infinity. So it looks like we have something that will do the right thing. Everybody got this? Now, before we go any farther, I want to point out, when people tell stories like this, you should be deeply skeptical. Because usually stuff like this doesn't work, right? This is like you're sitting there and you come along and it's not working and someone says, what's wrong? You say, oh, I can't solve ax equals b. And the person says, well, why? And you say, well, that's because my matrix A is singular. And you go, oh, well, gee, that's too bad. And then you say, what does it represent? You say, oh, some measurement apparatus, something like that. And you say, oh, is it the apparatus on the desk over there? And you go, yeah, give me a hammer. And you just tap the desk next to it, and you say, A is now non-singular. Everyone understand what I just said? Right? So, because if you take a singular matrix, and if you take a random perturbation, in fact, take any entry generically, take the 6, 7 entry, and add 1e minus 19 to it, and with probability 1, the matrix is now non-singular. Everybody following this? Right? Okay, so the question is, does that solve the problem? The answer is, well, no, of course it doesn't solve the problem. The matrix is now non-singular, but it still has a condition number. It has a condition number of like 10 to the 19. So all the problems you were going to have when it had a condition number infinity are still there. Everybody following this, right? So people who just come along and like perturb your problem. So look at this. Someone says, I want to solve a problem. This is my true irritation function here. It expresses how I feel about each fi. I mean, it expresses the semantics of a hard constraint. It says, if fi is negative or 0, I'm just totally cool with it. Totally cool. It's neutral. It means nothing to me. But if it's 1e minus 19, that's completely unacceptable. That's what the semantics is, right? And someone says, Oh yeah, no problem. Give me some sandpaper. I'll just go down to this corner down here and I'll just sand it off. I'll start with some number 80 sandpaper. Then I'll go to 120 and some 400 and everybody know what I'm saying, right? So you sand it off and someone says, what did you just do? And you go, oh yeah, your function is now differentiable. And it's no different from, I mean, for all practical purposes, the same as what you had before. Everybody following this? And you go ahead. Let's apply your Newton method on it. Technically, that's correct, isn't it? I mean, if you take something that looks like that, if I sand the bottom off, I have to sand the sides a little bit too to make it a barrier, right? I mean, actually, this does it effectively right here. I don't have to use sandpaper. It's just, I use 1 over t. I take t equals 10 to the 9. Everybody following this? Okay. And what's the problem with that? Like the guy who bangs the hammer next to the sensor suite? What's the problem with this? Why aren't we just done here? Or why should you be deeply skeptical? So your suspicion is, though, it's actually true that if I take t equals 10 to the 9, I get a pretty good approximation of I minus, right? One that one could even argue is close enough for any practical purpose. That's actually true. But the problem is that function is actually just about the worst thing in the world for Newton's method, right? Because it's not close to quadratic, or another way to say it is its third derivative is big, right? Or it's non-quadratic. I mean, or here's another one. Its second derivative changes wildly when you get near the barrier, right? And that's another way, of course, of saying the third derivative is big or something, right? So that says Newton's method will work, and it will take 10 to the 9 steps. Okay, everybody following this? Right. So I'm just saying you should be very skeptical about things like this, right? Because it just doesn't work that usually when someone walks up to you and you say you're having a problem and they say, oh, no problem, we'll just smooth this, we'll sand this thing off, and now it's differentiable, and then they walk away, you should be suspicious. I want to say that we have seen this story, you have seen this story before in a different context. And so let me tell you the context you saw it in. It was this. This is the function that really captures how we care about constraints. It's this thing here, right? But do you remember what happens in Lagrange duality? You approximate this function by this, right? And the slope there is lambda I. Okay? Now the point is, nobody would be tempted to look at that and say, yeah, that's a pretty good approximation, right? So, but the shock was that Lagrange duality kind of worked in some sense. That an approximation this bad of this thing actually yielded something. But at a high level, it's the same thing. The same story is behind Lagrange duality as behind, well, the logarithmic barrier, right? Because the story starts this way. This is what you care about, this thing. And then you say, let's replace it with something. In Lagrange duality, you replace it with something that's linear. And people say, wow, that is a crappy approximation. You go, yeah, but I'm leaving open the following possibility. I can wiggle the lambdas, right? That's the secret in Lagrange duality, right? What was weird is Lagrange duality ended up having like a really good ending, right? So so all I'm saying is the story is the same. Here, instead of saying we're going to replace it with a linear thing and wiggle with the slope, we're actually going to replace it with something that actually plausibly is or might be an actual approximation of this function. So, by the way, all this hints that duality is going to pop right out of what we're doing. And you shouldn't be surprised because the stories start the same way. In fact, at an abstract enough level, the stories are exactly the same. You replace the true irritation function, which is this thing, with some kind of smooth approximation. In Lagrange duality, it's the smoothest thing you can get. It's a line. Here, it's some log barrier. Okay. All right. Oh, so let's look at the log barrier function. Well, it's convex, so we know that. And its derivatives, let's work out what these are, right? So the gradient of this is, well, the gradient of minus log minus f is this thing, right? And remember, fi of x is negative, so this is a positive. So whenever you see minus fi of x, it's a positive number, okay? So this says that the gradient of the log barrier is a positive scaled sum of the gradients of the functions. Remember that. It's going to come up. That's what it is, right? Oh, and what are the scale factors? Depends on how close you are, how tight what margin you have. That's the margin. Minus fi is the margin in the inequality. You want fi less than 0, it's minus 0.2. Your margin is 0.2, right? Fi can increase 0.2 before you're infeasible. Everybody got this? So so this is 1 over the margin. So the scale factors in front are the 1 over the margins. Okay? And the Hessian looks like this. That's just for reference because we're not actually going to use that, but just so you know what it is, right? By the way, you see here a set of rank 1 terms and then the actual, the sum of the Hessians. Okay. All right. So if I take a problem and I minimize here, oh, by the way, we had to draw the picture, we were minimizing f0 plus phi of x. It's the same thing as minimizing tf0 plus phi. Why do we do that? Because the self-concordant stuff will work out later better or something. But it doesn't matter. I mean, in fact, most people put the 1 over t there. And by the way, they call it kappa too. So it doesn't matter. You'd figure these things out. Okay, so this says we're going to minimize tf0 plus phi. So to ax equals b. We're totally ready for Newton here. So we know exactly how to compute that. Nope, not a problem, right? Now, we do expect that when t gets gigantic, this is, Newton's going to have some trouble. We'll get to that. Okay, so this thing is, it turns out you can show that the log barrier is strictly convex as long as the feasible set is bounded, right? And we're going to just assume that. The feasible set is bounded, and then that says that the log barrier is strictly convex. So this is a unique point. And in fact, if you minimize this, that's called x star of t. And it's a path, right? Because for each t, you get a minimizer, right? And that's called the central path, the path of centered points or something like that. That's a central path. And so the picture would look something like this. We start with an LP. Here's 1 inequality, 2, 3, 4, 5, 6, whatever it is, 6 inequalities. And these dashed curves show you the level sets of the barrier, right? And it goes up to plus infinity, so you should be visualizing that the barrier goes up to plus infinity at the boundaries, okay? And then what we're doing is we're adding t times c to the point and minimizing. And so that's sort of the analytic center. That's the point that actually, the analytic center minimizes the sum of the negative log margins. That maximizes the product of the margins. So it's a point deep inside the set. That's the analytic center. So it starts here with t equals 0. And then as you crank up the scale factor in front of the c, it says minimize the barrier function, but also start putting a strong, now it says start minimizing t times c. C is the actual, c transpose x. C transpose x is the actual objective you want to minimize, right? So what happens is very interesting. Oh, what happens is the more you crank up t, the closer you come to minimizing c transpose x, but you will never leave the feasible region, right? In fact, you'll never leave the strictly feasible region. The reason is the barrier, which is, by the way, this is why it's called a barrier. The barrier goes up to plus infinity, and no matter how big t is, you'll move in the direction minus c. But at some point, you'll get to the point where it's no longer worth it to get closer to the boundary, and you'll stop. Everybody got this? So the central path might look like that. I mean, it's kind of silly because it's an LP in 2 variables or something. But anyway, that's what the central path looks like here. Okay, and that's the idea. Okay, so that's a central. Now, it turns out, if you're on the central path, surprise, surprise, you get for free dual points for the original problem. So let's see how that works. If you're on the central path, it means you minimize tf0 plus sum minus log minus fi of x. So you minimize this thing. And let's take the gradient of that right now. Well, you get t grad f0, and then you get the derivative of this. I'm going to ignore the second term, which is the equality constraint Lagrange multiplier part. That's this thing, but I mean, that just works. And this thing, the gradient of that, is this thing right here. Now you stare at that for a minute, and you realize, that's interesting. In fact, the first thing we're going to do, just for fun, is we're going to take this t and put it back over here. You know, frankly, it probably should have been there anyway, right? So we're going to get rid of that t, and we're going to divide this by t as well, okay? Okay, like that. That's what we're going to do. And now you look at this and you say, hey, that's interesting. On the central path, here's when you compute a point on the central path, strangely, you have the following. You have the gradient plus a non-negative weighted sum of the gradient, this is the gradient of the objective, plus a non-negative weighted sum of the gradients of the constraint functions, and then plus A transpose times an equality constraint dual variable, that's 0. That should sound familiar, because guess what? That's actually Lagrange duality. Because look at this. It says that if we take these numbers here to be the lambdas, and we take this to be nu here, then this thing reads grad f of 0 plus some lambda I grad f of I plus A transpose nu equals 0. But this first term is exactly the gradient of this with respect to x, right? So that's what it says. So this says something amazing. This says that if you compute a central point, whether you like it or not, what pops out are dual variables. Okay? Now remember that in a lot of cases, it's not easy to find dual variables, right? I mean, if you take like an LP, which works here, right? You can't just pick some positive vector and some other vector. I mean, there's equality constraints that have to hold. It's like A transpose lambda plus C equals 0. So the fact is that if you just pick a lambda in an LP, it's not going to be dual feasible. Or another way to say it is, you would say, here's my positive lambda and my nu, please tell me my lower bound, and it will come back and go, well, I got a lower bound for you, it's minus infinity, which is the universal lower bound, right? You don't even have to hear the question before you can give that as a lower bound, right? So it's not trivial to say that it's not to find dual feasible points or anything like that, but this does it, right? So any point on the central path gives you dual feasible point. Well, if you have a dual feasible point, you should have a strong urge to do the following. If you have a dual feasible point, you should think, that gives me a lower bound on the optimal value of the problem. So let's evaluate the lower bound. Let's find out what it is. So let's do that. Well, so we'll take this dual feasible pair, and let's work. It says simply that that's dual feasible. Well, I mean, this is true even if it's not dual feasible. Dual feasible means that this thing is bigger than minus infinity and therefore non-trivial, right? So let's work out what G is. Well, it's just L evaluated these points. But that's F0 of X star of t, and then plus some lambda I star Fi. But lambda I star is actually 1 over Fi of X star times t. They cancel. This is just M over t. It's nothing more, right? And so you get this. And it's actually extraordinary. That's G. And the duality gap, X star is of course strictly primal feasible, right? And it's got the value F0 of X star. But it says that when you center, if you do analytic centering, you get two things. You get a point which has an objective value, F0 of X star of t. But you also get dual variables that certify that this number is a lower bound on the optimal value. And the gap, people call that the duality gap, is exactly M over T. Okay? Everybody, it's crazy. I mean, it's just arithmetic here. I mean, not arithmetic. It's completely true. There's nothing complicated here, right? You just take some derivatives, make a few observations, and that's it. So that says, if you minimize T F0 plus this log barrier of x subject to ax equals b, then it says two things will come. When you write the Newton method or whatever from that, there'll be two return things. An x, which is strictly feasible, and a pair of dual feasible vectors, lambda and nu. And the associated gap between the upper bound on the objective value, which is that's f of x0, f0 of x star, and the gap, which is g of lambda star, nu star, the difference between those two will be exactly m over t. Okay? So that's cool. By the way, what this says is we now know that this kind of hand-waving intuition about, we looked at this thing, and I looked at this and I said, oh, hey, look at that. If t gets bigger, you get a better approximation to the true thing we care about, right? I said, so, I mean, it sounds reasonable if we take t big, you're getting close to the original problem, right? So that's all hand waving, and I can make up other stories like that, and they're totally wrong. This means it's actually completely correct, and it's very specific. It says that if you calculate x star of t, that is, you minimize this objective subject to that equality constraint, which we know how to do using Newton's method. Then it says the following. It says if you do that, then you will have computed a solution to the original problem, which is at most m over t suboptimal. Everybody got that? Obviously now if t goes to, as t gets bigger, you're done. So a couple more interpretations. This is actually probably the dominant modern interpretation. So the modern interpretation of if you look at interior point method, if you go, pull some book or something like that, I don't know. This is the way the story would go. They would say, here are the KKT conditions for an inequality constrained problem. Well, you better have that. That's primal feasibility, right? You have to have this, right? That's another one. And you have to have the following. Here, you have to have complementarity. And that says this, right? That's equal to 0. So I equals 1 to m, right? And this says that for each constraint, either the Lagrange multiplier is 0, right? And that must occur if that constraint has margin, right? If fi is actually negative, right? Then the Lagrange multiplier has to be 0. And you know that for many, many reasons, right? Or if the Lagrange multiplier is positive, the only other option, it says that constraint must be tight. And tight means fi is 0. So this is complementary slackness, I think that's complementarity or complementary slackness. Okay, so and we look at this, and then you have to have this, right? And so here's what's really cool: when you center with parameter t, here's what you get. You get something. You get an x star of t that satisfies this. As a matter of fact, it satisfies the fi of x is strictly less than 0, right? Because you're minimizing the sum of the minus logs and blah, 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 right? Okay, so you get this even with a little margin. You get a lambda that's strictly positive because it's like, I forget what it is. It's 1 over t times minus fi. And the fi is, well, okay, that's never 0. Okay, so you get satisfy this strictly, you satisfy this exactly. And here, instead of a complementary slackness with 0, the product of all the lambdas and the minus f's are 1 over t. Okay? Well, I mean, you can check because we defined lambda. Remember, we defined lambda as like 1 over t times minus fi. So that says that lambda fi is like 1 over t. So what it says, and now you can see, you can argue again, if t gets big, it says, so you're almost there. It's sort of, these you check off, right? So you get all of these. And the only thing here is instead of 0, you get 1 over t. And then the idea is we let t go to infinity. And we're now satisfying the KKT conditions. So that's kind of the idea. Oh, and you would hear, so if you actually find yourself hearing somebody talking about these things, I mean, I hope you don't. But if you do somewhere, then this will be referred to when you replace the complementarity condition, lambda I fi equals 0, with a 1 over t, which traditionally they would call kappa. Those are referred to as the modified KKT conditions. And so that story goes like this. Here's a problem, here are the KKT conditions. We modify the KKT conditions so that 0 becomes a kappa, and now we say we're going to apply a Newton step to the modified KKT condition. And guess what that Newton is? It's the Newton step for the problem we just looked at. So, okay, everybody got this? So that's it. Okay. And you can get some other interpretations. You don't need to know any of these things, but they're just kind of cool to help understand what it is. Here's one. So let's forget the equality constraints. Let's suppose you're minimizing f0 subject to fi less than 0. That's the log barrier, so let's center. You can think of it this way. I like to think of it as Tf0, that's the potential of a force field. And the force field is minus t times the gradient. Right, so it's actually a potential. And then minus log minus fi, that's the barrier term associated with fi less than 0. That's actually the potential of this force field, the force field which is 1 over fi times gradient of fi. right? And then the optimality condition for minimizing this is that, and that says that all the forces balance, right? So, and I mean, it's dumb. It's saying like, look, let's minimize, this potential plus these potentials, and each of these is a logarithmic potential associated with one constraint. Okay, so it's like a force field interpretation. And for a linear program, you get something even cooler, a very simple interpretation. The objective is just something like that, TC. And if you like, you could think of it like this. I have a constant force field in the direction minus c. It's like gravity, except the magnitude is t, and I can turn it up. So I can turn gravity up and up and up. And it's a constant force field. It just points in the direction minus c, and I have the ability to turn up gravity. Okay? Now, the other planes, the AI, those things, it turns out that this is the thing that's the force field associated with the logarithmic barrier associated with just AI transpose x minus b is less than 0, or AI transpose x is less than b, right? That's the force field. It's a beautiful force field. It always points away from the plane, and it's actually a beautiful thing. It's with exactly an inverse distance magnitude, right? So for example, if that's a linear inequality that says please stay on this side of the linear inequality, it says that the force field here will point away from this thing, and the magnitude will be inversely proportional to how close you are. Okay, so as you move closer, you get a very strong repulsive force, right? So it means like you've sprayed these planes with some repulsive stuff. I don't know, you have to find, I don't know. Actually, I don't think there's anything in physics that actually does this, but you can pretend like there is, right? So, by the way, it's not correct that you spray it with charge. There's no physical thing that will actually make the analogy right. So, at least that I know of. So, that's it. And now you can actually visualize what the force field is. It's very simple. For example, at this point, you're actually being acted on by five things, right? Five forces. But the force field is pretty much in that direction because you're right up under the shadow of a very strong one, and so that's dominating, right? And so what happens now is the analytic center is when you've got all these repulsive fields all around you, and you retreat to the center where all those forces balance. Okay, and now they all balance. I mean, that's this point. I mean, actually here it's not the analytic center. We've turned t up a little bit. It's t equals 1, right? And so it goes minus c. When you make this thing bigger, right, you move to a new equilibrium point. Okay, so this doesn't do anything. It's just a way to think of all this stuff, right? I mean, otherwise it's just too fast, So, and it's actually not a bad way to think about what these things are doing, right? So, okay. Now we get to the barrier method. So, and let me give a little bit of preamble. Okay, so simply choosing a big enough t, and minimizing using Newton's method, it actually isn't called, but I decided to call it that, the UMT. That's unconstrained minimization technique. And I'll tell you why I decided to call it that. It's because it's a weird retro historical reference. Okay, so that's the unconstrained minimization technique. Weirdly, it actually works fine. So it's actually an awfully good way if you're solving LPs, but to some relatively low accuracy, so t doesn't have to be gigantic. It's an excellent method. You write Newton method and you go at it. It just works, right? Everybody, so it just works, right? And it just always, you get the minimum, you get the duality gap, it returns primal point, dual point, everything, and the gap is exactly m over t. And if you wanted that to be 1e minus 3 or 1.01, right, depending on your application, that's exactly what it will be. Everybody see what I'm saying? Works pretty well. Now, it doesn't, if you ask for high accuracy or something like that, then it doesn't work. Okay, it works. It just takes 10,000 iterations if you implement it in infinite precision arithmetic. Right. So, okay. So there's actually a method, and it's a general idea. And so the other name for the barrier method, by the way, from the 60s, is SUMT. S-U-M-T. That's sequential unconstrained minimization technique. Beautiful name, right? Because it says exactly what it is. Well, except we added the equality constraints. But for all practical purposes, those aren't, so equality constraints don't hurt you. They're the unconstrained referred to no inequality constraints. Everybody got that? So that's a beautiful thing. There's a book written on this. like 1969, sequential unconstrained minimization technique. Okay, so, and if you just fix t and solve it once, that's now, I decided to call it oomped. Okay, so, all right. So now the sequential method, that's the barrier method, and it works like this. So you start with some point that's feasible here, and what you're going to do is the following, and some positive t. Now it's parameter mu. This is a very simple method, and you're going to do the following. You're going to compute x star of t by minimizing this thing, subject to a equals b. Then you're going to update. That's going to be your new value of x. And then you're going to quit if m over t, which is exactly the gap, is less than epsilon, right? And then you would return, by the way, both x and the dual points, right? Because that's what you should return. If you write a solver, you should return the dual points as well. Okay, and you increase t. Now, the key here is that you use Newton's method to minimize this, starting from the last point. That's the key. Okay? So that's the key here, right? And there's a name for this, and there's beautiful pictures for this. Like, so for example, another name for methods like this method, in fact, a method like this, another name for this beautiful name is path following method for optimization. Absolutely beautiful, because, here's the central path, right? Going into your solution, right? And a path following method says you're here. That's a certain value of t. Let's take mu equals, 1.1. Okay? Then what happens is, starting from this point, you apply Newton's method and you bump around for a bit, and then you end up there. And this is x star of t, and this is x star of mu t, right? So that's the new point. And you can see what you're doing. You're sort of following this path, right? So, and there's a name for these methods, and it's actually there's a very good thing to know about these methods. So actually, there's a beautiful, so the name for a this is something, again, you don't need to know this, but it's actually a very good thing for you to know if you do any kind of math or anything like that. There's a general family of methods for solving a hard problem, right? And it's called a homotopy method, okay? And the way it works is very simple. You have something you want to solve, like a set of equations, or for that matter, an optimization problem. But you have a set of equations you want to solve, and they're hard to solve. So what you do is you introduce a parameter into the equations. That it's a knob that you turn, okay? And it has to be continuous, or as you turn the knob, the equations deform continuously. And now the traditional ranges of these values for the knob are 0 and 1. And so the idea is when the knob is all the way up at 1, you got the problem you wanted to solve. That's the traditional parameter value. When it's 0, the idea is it starts from a simple problem. Everybody following this? Right? And then now the method, I'll describe a homotopy method, is very simple. Here's what you do. You set your knob to 0. You know the solution already. Then you set the knob to 0.05. Okay? Well, the problem is now close to an easy one, and you knew the solution for the easy one. So you use something like a Newton method to try to find it. By the way, what would you do if Newton method failed to find that point? Yeah, you'd back off. Instead of 0.05, you'd go to 0.025, right? Now, in this particular case, you don't have to, because no matter how you set this thing, it's going to work. Although it might take too many Newton steps. So you might do something like, I'll set it 0.05. If I don't converge in 15 steps, screw it. I'm going to back off. It means I stepped too aggressively along the path. Everybody following this? Okay. So then you're at 0.05, and now you set theta equals 0.1, and you apply Newton method again, and hopefully you get there. Everybody following this? And there's a beautiful book. I think the subtitle of the book on this is Pathways to, something like Homotopy Methods. The subtitle is Pathways to Solutions. I mean, come on, that's like too cool, right? This is a homotopy method, right? It's when, but there's a difference between a general homotopy method. In a general homotopy method, when you increase that parameter, you're actually not sure you can actually solve the problem. And there in a general homotopy method goes like this. If not solve problem, right? Then it says back off the parameter increase. Everybody understand that one line? Okay, so that's a general homotopy. Here, you can't fail, right? Because we can set t equals 10 to the 9, and at least in theory, we can fail. Now, there's a practical idea of failure. That might be that it takes more than 10, 20 Newton steps, right? So I just mentioned that. Okay, so here, so it's extremely simple. That's the idea. Now, mu, that's the amount by which you increase, oh, sorry, the typical homotopy method, the traditional parameter range is 0 to 1. 0 is your easy problem, 1 is done. Okay, so our parameter range is like 0, infinity, okay, or 1, infinity, something like that. Okay, so that's, but so what? That's a difference, but I thought I'd mention it, right? Okay, so now what we do here is you're going to increase t, which is actually a measure of inverse gap. You're going to increase t by a factor of mu. Now, if you really sort of followed the idea of, a homotopy method following the central path towards the solution, pathway to solution, if you really kind of follow that image, you would think of mu as being 1.05, right? You'd increase mu 5%, start and you'd hope for a couple of Newton steps and it's all over, right? That would be, and there's actually a name for methods like that. Those are called short step path following methods. Okay, so you Google that, you'll find 50 papers. Okay, their long step ones is where you're much more aggressive in updating the parameter. And the choice of that mu, which is how much you update the parameter value, that's sort of like how aggressively you update. There's a trade-off. If you make mu tiny, then presumably every time you're solving the new problem, it's basically the same as the problem you just solved. You're within the range of quadratic convergence. You do one step. And in fact, there are methods based on that. Those are the short step path following methods. And they choose mu so small that you're always in the range of quadratic convergence, right? So that literally you do 1 Newton step, increase mu. 1 Newton step, increase mu. So these are short step methods. Long step methods don't do that. Right. So, and it turns out actually that as a practical matter, different values of mu are actually better. 10, 20, 30. I mean, actually fairly aggressive ones, even 100 or something. Okay. Okay. So if you're gonna stop at duality gap epsilon, your duality gap when you finish centering is always exactly m over t. Right. If t has been increased by mu each time, you just take the log, base mu or whatever it is, and that tells so you know exactly the number of outer iterations to achieve duality gap less than epsilon. It's this, right? So it's kind of a beautiful thing. You can see that if mu is 1.05, that's a small thing in the bottom, right? And you take a lot of iterations. If mu is 100, it's a lot fewer outer iterations, right? Because actually, every time you do an outer iteration is a centering. So every time you do a centering, your duality gap goes down exactly by a factor of mu. So if mu is 100, that says you start with a duality gap of 100. Next step it's 1, then it's 0.01, 1e minus 4, 1e minus 6. Okay, that kind of thing, right? On the other hand, with mu is 100, you got some serious Newton heavy lifting to do, right? Because you're starting from one problem, but it's not that close to the next problem, and so who knows how many Newton steps you're going to have. And in fact, what happens in a general homotopy method, which is what you don't want to happen, is the following: as you approach the target, the problems get harder. This is what screws you, and this is, by the way, why it doesn't work to just go sand something off in any way you like. So that's what happens. If you just go, hey, I just learned this great idea, homotopy method. You don't have to know anything. Let me have your problem. I'll just sand these things off. I have a parameter that controls how much sandpaper I use. Oh, actually, it's the grit of the sandpaper, right? So I start with 80. I go to 120. I go to 400. I go to 800. This kind of thing. I guess they don't make grit finer. They probably do make grit for like lacquers and things like that go up to the thousands, right? But okay. So then, the problem, the downfall of a completely general homotopy method is very simple. It's that as you get closer to the solution, the problems get harder and harder. So you're increasing mu. Let's go from 0 to 1. Let's take a parameter theta going from 0 to 1. That's the traditional range. I go from 0 to 0.1, no problem. 0.2, 0.3. Now I start getting to 0.9, and instead of 2 Newton steps, it's now taking 20. And now I go to 0.92 because I've had to back off, and it's taking 100 Newton steps. And you can see this is not going well. So that's the downfall of why just constructing a general purpose homotopy fails. Okay, we're going to see something amazing happens here, and it's very specific to the log barrier and so on. Okay, so this is the total number of outer steps you're going to do, obviously, and then you're going to multiply this by the number of Newton steps required to solve the centering problem. Here, when t is mu times the previous t, starting from the solution when it was t. Okay? Now, if you use the classical analysis, something bad happens, right? If you go back to the classical Kantorovich analysis of Newton's method, you will actually find that these problems are getting harder. Well, okay, they wouldn't assert that because they understood well that they were simply producing an upper bound on the number of steps, which is valid. I guess they would say it, the correct way to say it is the complexity and that the upper bound is growing, right? So what would happen is when t gets very big here, L gets big, the Lipschitz constant. And we know that because what you're really doing is you're replacing something that looks like this with something that's curved, looks like that. L is going to get really big, and the prediction is that as you increase t, sure, the problems get harder and harder, and like first you're doing 10 Newton steps, then 50, then 100, and then it all falls apart. Everybody following this? Okay, so that's the classical analysis. But let's take a pause and let's just run the method and see what it looks like. So here's the method. Here's an inequality form LP, and what's crazy about it? So this is 50 variables, right? Here it is. Now, and I have to understand. I have to explain exactly what these are. This shows duality gap, and these are like little staircase plots. And what you have to understand is I'm counting Newton iterations here, and so the width of a tread is the number of Newton steps required, right? So I don't know. Let's look at this one. This one that's 20. That's like 8 Newton steps, right? These things. This is for mu equals 50, and that's for mu equals 150. Okay? Now the height of one of these stairs is when you finish centering, you just reduce the duality gap always exactly by mu, by a factor of mu. So on a log duality gap plot, you go down by a fixed amount. So the height of the stairs in each case is exactly the same. It's log mu. Well, it's mu on a log plot. Everybody's got this? Okay? So now you can see mu equals 2. By the way, we'll see that if you're doing complexity theory, right, so you want to prove that it's a polynomial time method, it will suggest taking like mu equals 1.01. What would it look like if it was 1.01 here? Well, first of all, it would be 1 Newton step for sure every time, right? And it would be it'd just be like a little staircase going like that, right? And it would go, it would work, okay? And but so what's weird here? So now you can see everything. Here's mu equals 2, and you can see that the treads are short, meaning you're taking 2, 3 Newton steps. I don't know. Here you crank this up to 50 and 150, and you're taking like 8 Newton steps, but you're making a big progress in gap, right? So, all right. Now here's what's weird. Let's just focus on this guy, like right here. You just reduced the duality gap by a factor of 10 to the 8. Okay, for all practical purposes, you just solved that LP. That is an LP with 50 variables, okay, with 100 constraints. That's a polyhedron that has got an absolutely gigantic number of vertices, right? R50 is a big place, okay? This says you just solved the LP in 30 steps, okay? Now, that's ridiculous. I just want to point that out. That means you're in 50-dimensional space. You actually stopped and asked for directions 30 times and said, excuse me, which way should I go? And the answer came back from some Newton thing or something like that, which is like go in that direction, right? That's what you did. 30 steps later, you have found your way to one of the who knows how many vertices this is, but the answer is a lot. You found you're very close to the vicinity of the optimal. Everyone following this? So that would be like in R3 asking for directions like twice or 1.5. I mean, you're asking for directions in a substantially fewer number than the dimension. Everybody realize how ridiculous this is, right? That's an R50. Here's what's cool. Guess what these plots look like if you do this with 50,000 variables? They look exactly the same. They're the same. Okay? They look exactly like this. It's the same thing. It's weird. Now, this is like a plot of the number of iterations you need as you vary mu. And something pretty weird happens. If you make mu too small over here, sure, you're going to take a lot of steps. By the way, if we continued this, this starts going up like that. Okay? But this is very cool because what's happening across this wide range of mu, this is super good news because mu is an algorithm parameter, right? And it's super good news because it means the good performance persists across a wide range. Now, what's happening here is very interesting. As you vary mu, as you increase mu, what's going to happen is the treads are getting wider. But the stairs are getting taller because you get more duality gap reduction every time you center. It takes you more Newton steps. Miraculously, you multiply these two effects out, and it's constant. Okay, everybody see this? And that's just a ridiculous number. I mean, 30 steps. These are, in fact, the numbers that you have been seeing for a whole quarter. If you pay attention, you probably don't, but if you paid attention to things like what's reported when Sedumi and SDPT3 run, is you can now actually understand most of the columns of what's being printed out. I don't know if you've noticed, but if you give it a super duper easy problem, it's 10 iterations. Usually it's 25. It can be 30, and if you give it some weird thing, some SOCP right on the boundary, and it, whatever, it can take 40. I don't know if you've been watching, but that's what this is. Right. By the way, a bunch of the other entries being printed out, you should also understand, because things like primal residual, dual residual, and things like that. So, okay, everybody. So this is actually pretty cool stuff. All right. So here's a GP. Guess what? It looks the same. Okay, just same. This is with log sum x. Bunch of log sum x. That's a geometric program. Here's a bunch of LPs. I think this is the problem you're going to solve, and this is what it looks like. This is for each one. You get 100 instances for each problem size, and you solve it. So this here is a problem with, I guess, 1,000 constraints and 1,000 and 2,000 variables. Okay, and you can see. By the way, in all of these simulations, the absolute maximum number of iterations was something like 30. That was it, 31. That's it. Okay, everybody, this is kind of the scaling. By the way, this scaling law continues. Oh, and I should tell you how this works. The theory, we'll get to it in a minute. The theory says this thing scales like the square root. That's the best bound known to date. Okay? It says that as you get bigger and bigger, the problem goes like square root. That's enough, by the way, for our polynomial time complexity theorist to be happy or something, right? So that's fine. This is the scaling. And I'll tell you a little, let me just tell you a little bit about this, and we're going to quit here for today, but I want to say a little bit about it. You see these pictures? Guess what? The pictures look the same if these are anything. LPs, QPs, actually, we'll see later, we'll extend this to do semi-definite programs, things like that, SDPs, SOCPs. It doesn't matter if it's a problem from signal processing, from control, from finance, from machine learning. They all look the same. And I was going to say something about this. This empirical thing continues because I have a friend in Glasgow who solved an LP in exactly this form with, I think it was something like 1 billion variables on some gigantic, ridiculous, gigantic machine, one of these IBM Blue Gene things or whatever, right? Okay. I just go ahead. I said, what method do you use? He said, just standard method. And I said, so how many iterations does it take? And the number? Yeah, you're close. It's 24. This is the amateur. What you're seeing here is the amateur implementation that's, yeah. By the way, all of these implementations you can find on the book website. You can find our code. But so the pedagogical amateur implementation gets 30. The really cool ones get 21, 24. So just 24 steps. It was identical, right? Now, I should ask something about this. This is the number of steps. But at the time for a step is not constant. Duh, because a step is actually solving a least squares problem. Everyone agreed? Because it's solving a Newton system. What's a Newton system? It's solving a least squares. It's minimizing a convex quadratic. There's another name for that. It's called solving a least squares problem. Everybody following this? Right? So the difference between this guy who solved a 1 billion variable problem and us solving a 100 variable problem, that's like over here somewhere, is considerable. I solved my 100 variable problem in 100 microseconds. And, each iteration for him, by the way, took something like 90 minutes, okay? And the lights in Glasgow dimmed while it was running, okay? and the downstream river was really hot or something like that. So, but the point was, it was just 24 of those. So it's 24 times 90 minutes, right? So actually, this is actually super duper interesting because what it says is the following. It's kind of weird. It makes full circle with the whole course back to least squares, right? So when you come into this class, you know about least squares. I mean, everybody knows about least squares. And you shouldn't make fun of least squares because like all sorts of crap is made to run really well with least squares. All sorts of image processing, like pretty much all of actual statistics that's used. I mean, right? All of control, all sorts of stuff is least squares. I mean, you throw in regularization and some other tricks. You fiddle with the weights. You can make a lot of stuff happen. And then basically 20th century engineering was done with least squares, okay? Period. And a lot now too. Everybody on board with this? And then you say, well, why do you take this class? And you go, well, you know, that traces back to Gauss. We're going to learn that you can do kind of the same stuff, but now have inequalities and constraints, and you can really say what you want. Everybody following? I mean, that's kind of what the class is about, right? Here's the joke. At the end of the class, someone says, okay, fine, I believe it. I can do monotone regression now. I can solve all sorts of sick things and, you know, crazy machine learning things with, I don't know, all sorts of weird hinge losses. You can do signal processing and compressed sensing, all this crazy stuff. I can do finance with like 3/2 power transaction cost model, all this crazy stuff. And someone goes, whoa, that's cool. How do you solve it? And do you know what this says? The answer is you solve 20 least squares problems. Everybody got that? So what this says is if you're solving, you know, the classical, you know, older mathematical engineer sitting there, what are you doing? LQR, I don't know, Kalman filter. And then what are you doing? Well, I'm adjusting some things like covariance matrices or weights or costs or something like that. They're tweaking it to make it work, right? So then they'd say, well, what are you doing? And you go, I'm doing convex optimization. I don't have to say these things are between 0 and 1, or I don't have to tweak things to make it between 0 and 1. I can just say I want these variables between 0 and 1. Everybody following the story? Okay. And they go, huh, how do you do that? And I go, by solving 20 least squares problems. So it's kind of embarrassing that they're so close. Now, so far we've assumed that you started with a point that was feasible, and we're going to fix that now. And we're going to fix it first in the absolutely classical way. This is from 1948 or something like that. So the question is, how do you find a feasible point if you don't know one? And lots of answers. Here's one way, is what we want to do is find a point x that satisfies the inequalities and ax equals b. And the truth is, if we really want to initiate a barrier method, these inequalities have to be strict, right? So it's not good enough to do this because the log barrier domain is these things strict. Or another way to say it is, if you're using a barrier method, Slater better hold. The Slater constraint qualification better hold. You better have a point that's strictly feasible. Okay, so here's your basic one, 1948, goes like this. You introduce a new variable s, and you minimize over x and s, subject to fi of x less than s and ax equals b. That's it. Okay? And I mean, and if you look at this, you'll realize immediately this is nothing but the epigraph formulation for minimizing the max. You're minimizing max fi, right? That's what this says. Okay. So what happens is clear. If you solve this let's discuss it. For this problem, you can easily get a strictly feasible point, right? So what you do is you pick any x in the domain of fi, right? You can actually relax the ax equals b or whatever, something like that. But you can handle that as well. Let's even just skip the equality constraint for now, right? But you simply take a point x. Then what you do is you choose s to be, say, the max of fi of x plus 1. And now every one of these inequality holds with at least a gap of 1 in there. Okay, so that gives you a strictly feasible point. So you solve this method. You solve this problem using, say, a barrier method. And what will happen is this. If the optimal S is positive, you're done, right? Because you now will have a certificate proving that there is no point that satisfies fi of x less than 0. And in fact, the optimality conditions here, you could reconstruct a dual certificate, and actually a theorem of the alternatives, an alternative certificate, right? So that's the case. Otherwise, you can terminate the minute S is negative, right? Because if S is negative, you break here, and you've computed a point that's feasible, that's strictly feasible. And then you switch to the barrier method. Okay? So this is completely it's classical. Okay. There's variations on it. In fact, I think on your current assignment where you're implementing one, there's even a more sophisticated variation where you take into account the equality constraint. So, okay. Here's a very interesting alternative. These are called phase one methods. I guess I should mention that the idea is there's phase one and phase two. In phase one, you determine a feasible point, and then in phase two, you then find an optimal point starting from a feasible point, right? So those are called phase one, phase two methods. Actually, most modern methods use a different thing which combines both of them at once. So here's another variation. Instead of minimizing the maximum of the functions in phase one, you minimize the sum of the violations. So if you take a look at this problem here, S should be interpreted this way. SI is something like a violation in F. It's how much extra slack you have to add to that inequality to allow it to be true, or something like that, right? So here you're minimizing the sum of the S's, and this is exactly equivalent to this. You are minimizing here sum of Fi of x plus. It's exactly that. So the sum of the positive part, right? By now, you should have a guess as to what that's going to do, right? Because in your head, you should see this. And I guess if you're in machine learning, you call that hinge loss or something. But whatever it is, it should mean something to you. What you would expect, and this is exactly correct, is that when you solve this problem, well, if there's a feasible point, you'll get every point here. But if it's infeasible, something very interesting happens. You might get a few points up here. Or another way to say it is you have sparse violations, right? So that's what this will give you, sparse violations. That's the idea. So here's a quick example. We have a set of 100 linear inequalities with 50 variables here, right? So it's infeasible. So there's no point that satisfies all 100 inequalities. If you apply the standard phase one method, this is the margin here, right? So if you're above 0, that means you satisfy the inequality. Well, what you've done in the basic phase one, the minimax phase one, what you do is you push all of them this way, and the result is, congratulations, you didn't push all the margins positive. There is no point with that. But what's happened is, of course, all the margins have piled up on the line where you're pushing, right? And so that ended up being, minus 0.2. So the point is, here you got 50 out of your 100 linear inequalities are violated, and actually there's a couple down here, so it's probably more than half are violated, something like that. Well, I guess it's here, yeah, 51. Okay, so 51 inequalities are violated. When you do this sum of inequalities, like this sum of violations method, you get something very interesting, and you can sort of see what happens. So, by the way, what it says is that many of them, right, are satisfied, right? There's a big bump right there. That's a whole bunch of things that ended up right there. It was just as easy. And you have a handful out here that are the ones you cannot satisfy, and so on. Now, this does not compute the point that violates the fewest inequalities, right? It doesn't do that. It's a heuristic for that, but you can see what it does. Everybody got this? So, and by the way, what would you say about that inequality right there? It's an easy to satisfy inequality. So not only is it easy to satisfy, it's easy to satisfy with a bunch of margin. It doesn't really cost anything, so it's done. Yeah. By the way, there's no incentive whatsoever for a margin to move to the right. None whatsoever, because the slope of the hinge loss is 0 once you've satisfied it, right? So, you could put a small slope on that if you cared, right? So, okay. This actually has got a ton of uses. For example, in engineering design, if you throw together a problem with a whole bunch of inequalities, a whole bunch of specifications, and it's infeasible, it doesn't really help you to get a phase one solution that violates like all of your 100 inequalities by some small amount. It's actually quite interesting to get one that satisfies like almost all the constraints but a few. So it hand selects a few, and it kind of guides you and tells you which of the constraints you're going to have to give up on, or it suggests which ones you could give up on. Okay. So there's a very interesting thing occurs when you're doing phase one. and it has to do with the complexity analysis of it. And in fact, this is the Achilles heel of the complexity analysis of all these interior point methods. So if you do real complexity analysis, this is, and you want to look and see kind of where the fraud is in complexity analysis of interior point methods, look for a constant that tells you how feasible the problem is, right? Because basically, it's a bit fishy. But let me explain what the idea is. Here, what you do is you construct a family of linear inequalities like this. Now, the fact is, if you have a bunch of linear inequalities and you run a phase one method, actually two interesting things happen. If the inequalities have a giant feasible set, it'll take like 10 steps and you'll have a feasible point and you'll stop. So if the feasible set is gigantic, you'll terminate very quickly because there's just tons of feasible points. You'll find one real quickly, okay? Now, the flip side also occurs. It's completely symmetric, and it goes like this. If the inequalities are wildly infeasible, right, which, by the way, would mean what in terms of the dual or alternative problem? It'd be feasible, and its feasible set would be big, right? So to be wildly infeasible, right, means that the dual inequalities are not only feasible, but have like a giant feasible set. Okay, right? What that means is there's tons of certificates proving those things are infeasible. Everybody following this? This is all complete hand waving, but it's actually good to know. Okay, so in that case, also phase one terminates very quickly because it terminates when it produces a certificate of infeasibility. So again, 8, 10 iterations, 20. You know, if it's a challenging one. Everybody following this? So, but right if you now make a parameter that takes you that perturbs the problem and makes it go from feasible to infeasible, right? And you tune that parameter right at the phase transition between feasible and infeasible. That's where it actually gets hard to solve, right? And this is actually intrinsic. I mean, there's nothing you can do about this, right? This is it's sort of obvious, it's intuitively obvious, and so on. So, so what happens? It turns out is it's extremely difficult to create a problem that will actually be hard for a phase one to determine feasibility or infeasibility, right? If you just generate, anything that will come up in practice will be totally, it will work just fine. It'll be 10, 20 steps, it'll be all over, right? Period, right? Actually, there are some pathologies, but that's a different story, right? It's a pathology and it's your fault anyway or something like that. If you're using barrier, the general pathology is that Slater is not satisfied, and that'll do the trick, right? But using other methods that don't care about Slater, you get the same thing like this. So what happens? So the only way to do is actually to very carefully construct it, and you can see what's happening here, right? The number of steps is taking you. That's 25 or 30 or something like that. It's a bit high, but doesn't matter. This is infeasible, and then this is feasible. And if you zoom in right as you transition between them, you get something like this, right? So now let's think about what these mean, right? This is saying, well, it's now taking 80 steps here to work this out. That's because this problem is infeasible, but it's infeasible in like the 7th digit, right? This problem is feasible in the 7th digit, right? And so, in some sense, this is of no interest whatsoever in any practical application, right? If your problem is feasible in the 7th digit, you got a problem. You have a serious practical problem. I mean, it's not going to work, basically. Whatever you think you're going to use it for is not going to work, right? And the same for infeasibility, right? So, but this is just to show you what happens here. So let's do the complexity analysis via self-concordance, right? And so the assumptions are that the sublevel sets are bounded. In fact, that follows from self-concordance, in fact. No, not quite, if you have a bounded feasible set. And we'll assume that Tf0 plus phi is self-concordant. And sometimes you assume this, for example, for t bigger than 1, right? Actually, we're going to increase t, so if it's true for any value of t and above, it will be true. For example, if f0 is concordant, self-concordant, this is true for t bigger than or equal to 1, right? If phi is self-concordant and f0 is. Now, this would hold for things like linear programs, QPs, QCQPs, geometric programs, things like that. Now, there are some cases where it isn't. Here's one. Here's a maximum entropy problem, right? And it turns out it's not self-concordant. But it turns out it's really easy to make it self-concordant. And actually, when you think about it, you'll realize it's even the right thing to do. One of the problems is there is an implicit constraint here that xi is bigger than or equal to 0. That's the domain of the entropy function here. Okay? And it turns out all you have to do is add that, and you're back in self-concordance land, right? The reason is to the function here, remember negative entropy is not self-concordant, but negative entropy plus t times the minus sum log xi, that is self-concordant, right? So when you add this constraint, this thing is self-concordant, right? So, or sorry, tf0 plus phi is self-concordant for this reformulation. And in fact, what it means is that xi equals 0 is a problem here, right? And what this says is you better make it explicit because that's actually not a barrier for it. That's not a function that goes to infinity as x goes to 0, right? So this says go ahead and make it, call it out explicitly instead of implicitly, and actually then the formulation works. Okay. Oh, and I should say before we even start the complexity analysis, I should start with a general comment. The barrier method works extremely well even when f0 and tf0 plus phi are not self-concordant, right? So works perfectly well, but if you really want to understand why, I mean, if you really want to understand why, it has to do with self-concordance and things like that. So, okay. So I'll go over the idea of this. Actually, it's a bit complicated, so I'll say just a few things about it, and then this is something that you'll want to go figure out for yourself. So what happens is we know the number of outer steps. That's easy. That's just basically log 1 over epsilon, right? Because you divide the duality gap by a factor mu every outer one. So the question is, how many Newton steps does it take? And the answer is very simple. You are going to minimize mu t f0 of x, right, plus phi of x. We're going to minimize this, starting from the minimizer of t f0 of x plus phi of x. That's what we're going to do, right? Because we've minimized this. That's x star of t, right? And then we're going to increment t by multiplying by mu. And then we're going to minimize this function. So starting from the minimizer of this function, we're going to find the minimizer of that. And Newton's the complexity analysis of Newton's method via self-concordance tells you that the number of steps is less than or equal to this. It's a constant times the starting value of this function, that's this here, minus, if you put a plus there, that's minus the final value. So x is the current point, x is the minimizer of this, x plus is the minimizer of this. It's for the new value of t, which is mu times the old t. Okay? So it says you simply say it's the starting function value minus the final one, and then multiplied by a constant, and then plus c, where c is 6, right? Or log 1 over epsilon, I mean, whichever, right? So that's what it is. Okay, so we have to bound this. Now, we already know what's going to come to our rescue here because it looks like a weird circular thing that's completely useless because it says how many Newton steps does it take, and it says, oh, no problem. It's your function value minus your final function value. And you say, well, how do you find the final function value? You say, use Newton's method. But then if you run Newton's method, you know how many steps it is, and it's all silly. And of course, what's going to come to your rescue is duality, right? Of course, right? So I'll go over a little bit of this. It's probably a bit too complicated to do in lecture, so it's the kind of thing you have to work out on your own. And I'll just say a couple of things here. So here, when x is the minimizer of this, and we define, if you remember, lambda I to be 1 over t times minus fi of x, right? And these are dual feasible points, right? And in fact, they're the ones that give you the duality gap exactly m over t. Okay? So now we simply go through and make various substitutions, and I'll say a little bit about each one, but won't go into too many horrible details here. So this says, for example, that you can you can take phi of x here, right, and write it. You can write phi of x here, which is the minus sum log minus fi, and you can write that as minus sum log minus fi actually has the form 1 over ti lambda I. And if you're listening, and if I said it right, which is not clear, then the minuses go away, and that's like sum log ti lambda I, right? That you shove into this, right? This thing is, that's minus sum log minus fi of x plus, and you put those in and you get this thing like that. The mu is pushed in and then taken out here, right? Because the mu is this, you just take the mu out, you get m log mu, and that accounts for it. Okay? So, by the way, we've already used duality. This is where if you wonder where the duality it comes in right there when we did this. Okay, so in the next step, you simply use the fact that, log x is here is less than or equal to x minus 1. So we do this here. This is log that. We write that out here. And now a pattern starts emerging. You see mu t f0 of x plus minus mu t times sum lambda I fi of x plus. And you say, oh, hey, that is the dual function evaluated at, that's the dual function evaluated, or that's the Lagrangian evaluated at x plus, right? So, okay, so then, and that has to be less than or equal to the dual function there, because that is the minimum of this over all x, and in fact is minimized by x. So you get something like this here, and now you're very close, because f0 of x minus g of lambda nu, this thing, that is exactly the duality gap. It's exactly m over t. The t goes away, and you end up with a very, very simple expression like that, right? Now, mu is bigger than 1, and if you plot this function for mu bigger than 1, it looks like this, right? So here's mu equals 1, and what it is, it starts quadratic, and then it kind of ends up going up kind of linearly. I mean, it's a little sublinear because of the log, right? But basically, it's linear. But it looks like that, okay? Actually, here's the really cool thing about it. When it finishes, something really weird happened. Everything went away. It has nothing whatsoever to do with the dimension. The number of inequalities comes in as m up here. So it's very simple. It's just proportional to m and mu. That's your parameter. And notice that this predicts something. Actually, in some ways, we're already done, right? Because what this says now is it says that the complexity of incrementing t by a fixed factor mu, and then using Newton's method to minimize, doesn't get harder as t gets bigger. That already says this. Everything's there. It has nothing to do with t, nothing. Everything went away. And it even tells you more. It tells you that, for example, if mu were kept small, this number would be very small, right? It would be like, 1. And there's names for those methods. You can choose mu so that, in fact, 1 Newton step will suffice, right? That would be even less aggressive. I don't know if you remember our examples where we had things that look like this here, right? So something like that, mu equals 2, that's pretty aggressive. But if you had mu equals like 1.05, it would just be 1 Newton step per iteration, right? It'd take you a long time, but it would be 1 Newton step per iteration. And that's actually predicted exactly by this right here, right? So, and then it says as mu gets bigger, you pay approximately linearly, okay? So now you're ready for the final assembly, because that's our incredibly simple, and by the way, notice completely explicit bound. It's not one of these nonsense Western bounds, right? That has all sorts of constants you don't know, you'd never be able to know, or anything like, you could never evaluate, and it just makes you feel good because, but you see it's a polynomial or something, and then that's good. Everybody know what I'm talking about? So this is completely explicit. It's a number right there. I mean, 1 over gamma is 11. If you do the fancy analysis, it's more if you don't. C is 6. Just 6, period. Right? 5, 6. Okay. This is the number of outer steps. That's the upper bound on the number of Newton steps required to actually carry out the centering. And you get really cool stuff. This thing starts when mu is near 1. This thing is like quadratic. Then it accelerates to linear. That's this term. Okay? This term is really cool. It's got a 1 over log mu in it. So as mu gets close to 1, this thing gets big. And of course, this thing getting big makes perfect sense. That says you're going to do a lot of outer iterations, but each one is going to be super duper cheap, right? So, okay, so you multiply the two together and you get a function that looks like this. So that's what, and this is, I'm using our bound, which is pretty poor. I think it's 1 over gamma is 365 or something like that. And this is for like 100 inequalities and stuff like that. But the point is it actually kind of it tells you something. It says, for example, that you should use mu equals 1.02. There you go. You should increase the homotopy parameter by 2% each time. And this says you'll absolutely do, for sure, less than 10,000 Newton steps. Okay? Right? Total. Right. Now, we know, empirically, you're going to do 20, maybe 30 or 40, right? So something's off here. By the way, if you replot this using not the upper bound, but in fact the typical values, I don't know if you remember that, but you can just change this value of gamma. I think you change it to like 1 or something like that. It turns out if you do that, you actually start getting predictions that are completely reasonable. You should set mu equals 50 or 100 or something like that. Of course, it depends on m and all that kind of stuff. So it actually does predict everything. But most importantly, it just gives you a bound that doesn't depend on anything that you don't know. You know everything in this bound. Now, the numbers are big, but, it's a bound. Okay. Now, if you go back here and you look at this thing, and you ask yourself the question, I'll minimize mu, right? Of course, m is fixed. Your initial gap, that's m over t0 epsilon. That's something that's known. So for a fixed m and fixed, other thing, the Newton parameters fix gamma and c. And what you do now is you optimize over mu, and here's what you get approximately. It says that mu should be 1 plus 1 over square root m, right? Now, in practice, you would never do this, right? You'd have mu equals 100 or something like that. And later, I'll tell you, in fact, what, how this is really done. Someone already hinted at it earlier. Mu is actually mu is adapted every step, right? But roughly. So this says if you do that and if you work out what happens, it turns out that the total number of steps it's O of square root m, right? So this is sort of the crowning achievement, right, of the complexity analysis of interior point methods. This is for the barrier method, but it's true for every other interior point method. It's just O of square root m, right? Whereas, as a practical matter, it's observed that it's actually O of 1, and much more specifically, it's like 20 to 80 is what the number is, okay? Okay, so that's sort of the crowning achievement of the complexity analysis. Okay. Now, what's interesting is that this number, of course, is multiplied by the cost of a Newton step. But a Newton step is a least squares problem. So you have to solve a least squares problem every step. So it's actually quite interesting. It basically says, so the bottom line is if someone says, give me the executive summary on interior point methods, you'd say, oh, no problem. Again, this is, as a practical matter, it would be something like this. You'd say, it can solve a convex problem with constraints. It'll take about a few tens of iterations. Each iteration is solving a least squares problem that inherits its structure from your problem. Everybody get that? So that's the executive summary. What's bizarre is that's also true for a lot of other optimization methods that we won't look at in this course, right? So a lot of other methods like operator splitting and other things, same story, right? It's also kind of interesting because it puts it all in perspective, right? It says that after a century or more of people using least squares and twiddling weights to make things happen, it says basically that's what an interior point method is doing. It's solving 20 least squares problems, but then it solves an LP or some complicated other fitting problem you have, and it did exactly what you wanted, right? So I think it's a very interesting observation. Okay, so our last topic is to generalize interior point methods to, we're just going to generalize it to generalized inequalities, right? And you could have guessed that everything was set up to do this, right? So there's actually only one thing we have to do. I'll say what that is in a minute. So yeah, everything is set up to have kind of very powerful notation. so that the notation suggests what you should do. And there's only one thing we'll really have to do. So here's a generalized problem, and the difference here is that these functions return vectors. And then those vectors are not just less than 0. They're less than 0 with respect to a cone, ki. Right? Now, if the cone is like the non-negative orthant, this is kind of a fancy way to have ordinary inequality, so it's not interesting. It is very interesting when ki is something like, for example, a positive semi-definite cone, right? Because then this, I mean, really, that's the most significant example of a generalized convex problem, right? Is something like semi-definite programming, right? So, all right, so we have to reinvent everything to work in this case. Actually, it's going to be shockingly easy, right? There's only one real thing we have to do. Okay, so the main thing we have to do is to work out what the log is, right? Because in fact, what we want to do is we want to write down Tf0 of x plus sum minus log minus fi of x, right? And then we want to say minimize that. We're going to call that x star of t. And when you minimize that, then t times equal, then we want to say t times equals mu. Okay, and that's our, in fact, we want to run the exact same algorithm we have before. The only one minor problem here is that this makes no sense, right? So you have the logarithm of a vector. Okay, so that's the only thing we have to do is generalize the log to vectors. Now, by the way, you can almost guess what this is going to be. Like, what do you imagine is the generalization of log to positive semi-definite matrices? I mean, you get 3 guesses, and the first 2 don't count.
Log det.
Yeah, of course, it's log det. So it's going to turn out to be log det. So that wasn't so hard. Now, by the way, for the second order cone, it's less obvious what it is. But yeah, it's going to turn out to be our friend log det, right? And that's going to be good because that's self-concordant and all sorts of other stuff. So if you were just looking at semi-definite programming, it would be obvious what it would be. It's log det. So let's take a look at what you need to do. Okay, so you have the idea of a generalized logarithm, and a generalized logarithm for a cone, it's something like this. It says that the domain is the interior of the cone. I mean, that's the same as the domain of log is r plus plus, right? It's positive numbers. Well, the domain of log det capital X is positive is s plus is Sn sub plus plus, right? Set of positive definite matrices, right? So it's the same. And let's see, this says, well, it's concave, right? So we're going to require it to be concave, like log, right? We'll say a little bit more about that in a minute. And that's the idea. So it has to, the domain is exactly the interior of the cone, just like log. Okay, and then here's the interesting one. Along any line, it has to be the log. So it has to look, if you restrict to a line, it looks like a log. That is actually exactly what happens for log det, right? If you restrict it to a line, that's a line going through the origin, it actually looks like the log. It's exactly the log. So, okay, so it has to have the following form. If you scale it, it's an additive term, but there's a coefficient in front called theta. That's actually going to play a big role. It's called the degree of the logarithm, and we'll see what it's going to be obvious things. So here's the non-negative orthant, just to make sure this all makes sense. And here we take the logarithm on the non-negative orthant is the sum of the logs. I mean, this is kind of dumb, but fine. And then you check that if I scale a vector, right, what happens? If I scale a vector, I scale every component. And so what happens is, basically what comes out is theta, if I scale by s, what comes out is n log s, because each of these contributes you add something which is log s, and then you get n times it. So the degree is n. By the way, there's a beautiful interpretation of what the degree is. It has to do with the geometry of the set, and it's the maximum it's something like the maximum number of scalar constraints that are active. We're not going to look into this here, and that's true for the non-negative orthant. When you get down to the point 0, you've got like n planes coming in, and that's why theta is n. Okay. For the positive semi-definite cone, we take log det, and sure enough, everything works there. The theta is n. That's a surprising theta because the dimension of the positive definite cone is n plus 1 over 2. So if you really call that n, if you call that n, then basically it says theta is square root n. For second order cone, this is the logarithm for a second order cone is actually interesting. It's this. It's actually the log of, and then you simply form this quadratic form. What's a bit shocking about this and would kind of make you nervous, it takes you a while to get used to this, it's a bit more sophisticated, is the following. This is a quadratic form. That's a quadratic form. What's the signature of the quadratic form? Is it positive semi-definite, negative semi-definite? What is it? Convex, concave? You should be able to see it. Just look right at it. It's diagonal. And what's the diagonal matrix look like? It's got a bunch of minus ones. And how about the last entry? It's plus one. So this is a quadratic form. But it's not concave. It's not convex. Okay? So this doesn't, everyone see what I'm saying here? So you have to get used to this. This is right. But the log of that is actually concave. Okay, so this is one of those small subtleties. But it's actually worth knowing. This is it. It's not. This is not obvious here. And by the way, that definitely does not come from one of your composition rules, right? Because the argument to log here is neither convex nor concave, right? So this comes from the structure of this particular thing. Okay, so that, and actually if you look at it, it's actually really cool what it represents. That represents the margin in the second order cone, right? Because second order cone says that the sum of these things is less than that. And so this is the margin. It's how, in fact, probably it's close to a distance to how far you are from the boundary. If this is the second order cone going up like this is probably something like the distance. I mean, you might normalize it or something like that, but that's what it is. Okay? Everybody got this? So that's the idea. And the log of that is concave and satisfies this, and its degree is 2. Period. Okay. Okay. So here's some properties. And these are things, some of these are easy. Most of them are, actually, they're pretty easy to show. First is the generalized logarithm is actually monotone, right? So monotone, if you remember, means that if one thing is bigger than another, then the function value of the first is bigger than the function value of the second. It's monotone. Log is obviously monotone, right? So, but in fact, to express that in terms of the derivative, it's that the gradient should be non-negative in the dual inequality, right? So just to, that's what it is. So this says it's monotone. And what this says is that y transpose times the gradient is just theta. It's constant, right? That follows from this log thing and the homogeneity property. So for a non-negative orthant, the gradient is that. It's monotone here. And I mean, this is always positive here in the dual inequality, which is the same as r plus to the n. And you get exactly that. Yeah, that y transpose this is just n. For a positive semi-definite cone, the gradient is, I mean, with some conventions about how you represent the gradient of a matrix, the gradient is the inverse, right? That's, well, I mean, actually, that's kind of the analog of log. Derivative of log is 1 over. So for log det, it should, by aesthetics, be something like 1 over. So it's the inverse. You have to be very careful as to what exactly you mean by this, though. But so that's what it is. So the gradient of log det is the inverse. The inner product, right, of y and the gradient, well, the inner product of two matrices, the natural inner product is trace of the product, and guess what? Trace of y times the inverse is n, right, which is theta. Okay, so for the second order cone, the gradient looks like that. That's the gradient. So that's the gradient. And in fact, if you work out y transpose times the gradient of y, you get 2. Okay, so this is the idea. These are the main logarithms we're going to use. There are actually some exotic other logarithms for other sets that people use, and it's although they give better complexity results in some cases, it's not at all clear that they have any use in practice. I mean, they give any advantage at all. Okay. Now we can continue the analogy. So we're going to first talk about the logarithmic barrier for a set of generalized inequalities. It's the same thing. You simply form minus some log minus I. And by the way, if these cones were all the same, Or we could even write this as log sum I. That would be very cool overloaded notation, right? Very evolved notation, right? Because if you, in fact, you could even write just log there. So it would look exactly the same as for the scalar inequality case, right? And then it would be overloaded, meaning log has a different meaning depending on the type of its argument. If it's a scalar, it's your old friend log. And if it's something in a cone, it refers unambiguously to some logarithmic, some generalized logarithm for that cone, right? So, for example, log of a matrix would then be interpreted as log get. So, anyway, that's what this is. That's just a barrier function. It's convex. Why is it convex? Well, I mean, again, you needed all those properties. You use the following. These things are concave and they're increasing. That's convex. So this thing here is actually, by the composition rule, that's actually going to be concave. Sum is concave, minus turns it to convex. Okay? It's just the same as before. It's the same reason minus sum log minus fi is convex in X. Okay? So the central path is then simply this. It is the set of minimizers of tf0 plus phi of x subject to ax equals b. That's the central path. So it's identical, right? It's the same thing. Oh, and properly generalizes, right? That if these were all simply r plus, then this would reduce to what we have already seen. Okay. Well, then everything else just works, right? So if you write down what it means to minimize this thing, well, that's simple. It says that the gradient of this plus nu times here, h plus a transpose nu is 0 and ax equals b. Those are the KKT conditions. And so you get something like that. Not I called it w, not nu. Okay, so this is the condition. It's a bit harder, but you stare at it for a while, and you get something pretty cool here. What you realize, you divide by t, and then what you realize is that you take lambda I star, and that's going to be this thing. But remember, we have the following property. The gradient of the generalized logarithm is dual positive, right? That's the same as saying for a log, right? Its derivative is dual positive, but that's silly because it's the dual of r plus is r plus, right? So here we're using the fact that it's dual positive here. Okay? And then what this says is that if you center here, then basically it says that you minimize this Lagrangian here, where lambda star is this thing, nu star is that. That's identical to the other case. And you work out the duality gap, and you get the same thing. You end up taking the gradient of this, transpose this thing, and you know what you get? You get the sum of the thetas. So it's just, the calculation is identical, and you get this. What's really cool about this is, so this is the analog of m over t that you've seen up till now for the scalar inequality case. And in fact, the scalar inequality case is a simple case. You just say that you have a problem, you have fi less than 0, but that's a scalar. Then you'd say, well, the generalized logarithm we'll use is the logarithm, and it has degree 1. And so you sum up 1 m times, and you get m over t. So what it says is that this is what plays the role of what was m over t. And in fact, it's really cool. It says sum of theta. You can even think of that as something like as the effective number of scalar constraints. That's an excellent way to think of what theta means. Okay? So from now on, an LMI, roughly speaking, counts as n scalar inequalities. A second order cone counts as 2, right? A scalar inequality is 1. Everybody see this? So you could actually then take a problem, a cone problem, and say this has 237 effective scalar inequalities. That's simply the number here that plays the role of what's just m if, for example, all the inequalities were scalar. Okay, everybody got this? So it's actually cool. Okay, so we get to semi-definite program. So here, I mean, this is the most important case. So here is one in inequality form. We're going to minimize C transpose X subject to f of X is less than or equal to 0. The logarithmic barrier is log det of minus f of x inverse, right? So the inverse is the same as putting a minus in front of log det here. The central path is to get x star of t, you minimize t times the objective plus this thing. And if you take the gradient of that, you get here tci minus, this is the partial derivative with respect to xi, and this thing is, well, the gradient of this is like minus f of x inverse, right? And then you would, if you want to know what is like partial f partial xi, this is very rough, but that's fi. And so you'd put trace fi times this, and you get this inequality here, this equality here, right? So that's the optimality condition. You get a dual feasible point because this thing here, if I multiply by minus 1 over t, that's dual feasible, and I get a point z that satisfies that. This is the inequality form SDP, and the dual is the equality form here. And if I'd simply minimize this function using like Newton method, I get now a dual feasible point. And the duality gap is, it's really cool. You just work out what it is. That's the dual objective, primal objective. You subtract them. That gives you the duality gap, and that turns out to be, just using this formula here, p over t, where p is the size of the LMI, right? So that's it. So I mean, these are it's kind of, I mean, this stuff has been, I guess it's been well known for maybe 15 years now, 20 or something like that. But 20 years ago, not that many people knew about this kind of stuff, and a lot of people didn't. So now we have the barrier method. Here's a hint. It's identical. So it's exactly the same. There's only one change. I mean, what's happening is different. The only difference is that this used to be m, and now it's some theta I, right? So that's all it is the sum of the orders. So otherwise, it's absolutely identical to the other barrier method. I mean, of course, it was set up that way, right, so that it would work out. It didn't just happen. And that's it. And the number of outer iterations is the same, except that instead of m, you have, of course, the sum I over theta I. And actually, all the complexity analysis holds immediately. It all just works. It's all exactly the same, right? So you have polynomial time complexity for solving SDPs and things like that. Okay. So let's look at some examples. Now, when you look at these, your first impression is that it's the wrong figure that's been included because it looks exactly like the other ones, right? So, but it's not. I mean, it's not. I mean, these things all do look the same, right? So I guess that's good. So it means it's exactly the same. These plots look the same. This looks the same. By the way, this would also up here start going up like that, right? So they look the same as, for example, LP. So actually, it's a very nice set of generalizations and overloadings of meaning and things like that, because it's not just that the code, if it was written nicely, would look identical. It's more than that. Actually, the way it all works would be the same. In fact, even the empirical, the way it would work empirically would be the same. So let's just take a look at one of these. Here is a semi-definite program with 100 variables and a single LMI constraint with 100 by 100 matrices, right? So if you want to picture something like that, you're bounding some covariance or something, matrix or something like that with 100 variables or something. It's not a simple problem. It's one that 25 years ago, absolutely no one would have any idea could be solved by any method, right? Let alone by something like 20 steps of some quite simple method that's probably only like 15 lines or something like that. So it's quite a complicated problem. And here you can see that you're actually, with this very simple barrier method, you're solving it in things like 20, 30 steps, right? So real methods would do it in 20 or 18 or something like that. Each step is solving a Newton system. Any guesses, just for fun, just to see what the complexity of the computational complexity of a Newton step is here? Turns out it's end of the fourth. That's still pretty good though, right, for a semi-definite program. It's end of the fourth. It turns out that it's actually not solving the Newton system, which is order n cubed. It's actually assembling the Hessian in the general case costs n to the fourth. So that's actually what the computational complexity is. That's still quite good, right? Because it could have been like the dual has whatever 5,000 variables. That would be n to the sixth or something, because you'd have n squared variables, and then you apply Newton's method to that, you get n to the sixth, right? So, okay. So anyway, so these are this is all like it's very impressive that this stuff works. So here's a family of SDPs. It's like the family of LPs, and for each of these, you solve. That's actually a very specific SDP. But for each of these, you solve 100 random instances. And actually, it's not at all clear what happened out here at 1,000. But I guess it suggests that it's being reported honestly. But probably that's some numerical issue or something like that. But it'd be nicer if it just looked like it did for the LPs and kind of just go like this, right? That would be better, right? So, okay, so it's the same sort of thing. I should say that SDP is still kind of an open. It's no one has. It's not completely nailed yet how to solve SDPs. There are plenty of sort of SDP solvers. There are all sorts of special ones for different structures and things like that. People solve very big ones. For example, people who work on combinatorial optimization and need to do SDP bounds, they solve big ones. But there has not emerged what you have for things like LP and SOCP, which are simply kind of the best methods that just work. This has not emerged. So it's something people have been looking at for maybe 20 years now, and it would be really good if someone were to like figure out good universal methods. So that was a hint or a suggestion, a plea, one of those. So okay. So the last thing I want to talk about today are primal dual interior point methods, right? So in fact, the barrier method is not really used. Actually, it is in a few weird places, right? And in fact, it's even simpler. Barrier method with a fixed value of t is used in a few real-time things, right? Where you don't need high resolution, and you just use Newton's method to solve something like that. But generally speaking, people don't do this. What they really do is they don't even distinguish between inner and outer iterations. It's equivalent to changing. Another way to say it is you change t every step of every one is a Newton step, and you change t every single time. Instead of we go like 8 steps, satisfy a convergence criterion, then it's t times equals mu. And in fact, the way real ones work is they do a little bit of work to update t every single step, right? So that's one way. And they also, but however, each step always nothing but solving a set of linearized KKT. So the equations look like basically identical. And they use infeasible start Newton type things. So you don't have a phase 1 and phase 2. So these are kind of the standard methods. But the cost per iteration is identical to the barrier method and things like that. So they would have kind of some minor advantages, but not huge big advantages.